All right, hello everyone. Welcome to our Sweet Prime Talk. So pizza, we are currently tracking down. Hopefully, it'll be here soon. But in the meantime, we have a talk from Wes Johnson. He's a second-year PhD student here at CU Boulder, and he is going to tell you all about his research. So let's give it up for Wes.
Hi everyone, my name is Wes Johnson, and I work with Scott Parker. And today we're going to talk about, if you can't tell from the title, laser cooling and ion traps. So, we're going to get started. I'm not sure.
Yeah.
Not by the laser. So if there's cooling provided by the laser, we'll talk about it. So what I'm going to do first is I'm going to explain like what a pinning trap is, its basic setup, its historical relevance, and the pinning trap that I simulate is. Then I'm going to try and explain Doppler laser cooling in a very fundamental way. It doesn't involve any too technical terms or things like this. And then I'll discuss how it's implemented in our ion trap. And then towards the end of the talk, we'll discuss these crystal eigenmodes. So the crystal you can form in these ion traps by having many ions interacting. Different ways you can tune their geometry. And then I'll discuss very briefly what I've done to linearize the dynamics of this crystal, so it's easier to understand and easier to study the Doppler cooling effect on this crystal. And then I'll conclude with some results and tell you a little bit about myself and what I do. So first let's discuss the history. So there's a man, Hans Demo. He was a Nobel Prize winner in 1989. And this is just an excerpt taken from his Nobel Prize talk, discussing why he chose the pinning trap for his research. There's also someone that you guys may have heard before, David J. Weinberg. He got the Nobel Prize in 2012 for trapping ions and cooling them, and allowing methods to interact just individual quantum systems. So there's some Nobel Prizes involved with this type of research. There's some very precise measurements. For example, the G factor of electron, which is known to many significant digits, is when this experiment can be carried out in a pinning trap. And then the idea of having a single isolated quantum system that's not interacting with the environment, you can study effects on is very important, which is why Hans Demo coined this term geonium atom. It's basically you've got an electron or maybe some ion bound to the Earth, the geo coming from Earth. So there's a ton of different experiments you can do with this. So you can see in the bottom left, we've got confinement and cooling, but there's also plasma ion crystals, which is what we'll be talking about in quantum information processing, which is what the people in this are very interested in. But there's a whole zoo of experiments to do. So first, what is it? I mean, how do you trap an ion? This is kind of a non-trivial thing. We're going to discuss why. So we have this potential that looks like this, and if you can't look at an eyeball to figure out what that is, it's basically the salad shape, right? So if you imagine you're some particle sitting here, you might move back and forth in the z direction, but your motion's very unstable in the radial direction, so you just drop off, and you won't be in this trap any longer. So the question is, well, why don't we just make a bowl potential? Why don't we have a bowl potential so we can trap this particle? Well, it turns out if you take in electricity, electromagnetism force, you know that this equation has to satisfy the Laplace equation, and that basically gives us a constraint. It tells us, no, you can't have that bowl. This is related to something called the Earnshaw's theorem, but it basically says you can't trap a particle with just an electrostatic field. Well, what do? You add another field. So in this case, you have the magnetic field. And what this magnetic field does is when the particle tries to leave the trap, it feels a force that basically moves it along, like at some fixed radius. So it provides radial trapping. But this motion is kind of interesting because it's not confined in the sense that you have some potential. It's like keeping your particle locked. It's very different from that. Yeah, so there's basically three types of motion in the spinning trap. So the first type of motion is just through this magnetic field. Whenever you put a particle in a magnetic field, it will undergo something called cyclotron motion, where it oscillates around the field line. And in motion perpendicular to this, there's a harmonic motion due to this electric field that we've applied, which causes the particle to oscillate up and down. And then there's a very interesting motion called the magnetron motion, which is due to the relationship between this electric field and magnetic field. And that has a very low frequency and it's related to stability of the trap. So this is basically, if you haven't seen, this is what harmonic motion looks like. You have like some sinusoidal oscillation up and down in the trap. And so some ion, when I place it in this trap and I displace it from the center in z direction, it's just going to oscillate up and down. The other motions are a little bit more interesting than that. This magnetic field kind of complicates things. I guess that would be one of the main things we taught. So if you have this magnetic field, you have a frequency of oscillation omega c, where these particles just oscillate around in a plane perpendicular to the B field. And so what's not shown here is, of course, there's still this axial electric field, which will cause them to circulate up and down. So kind of like a helix like this. This is ignoring, of course, the electric field in the planar direction. So we have another frequency, one of our three main frequencies, and that's the slowest of which, the magnetron motion. So there's actually a drift that's caused in the plane by this electric field. So if you can see here, these ions, they're still undergoing that cyclotron motion, but now they're going to move. And they're going to move in a direction that's perpendicular to both the electric field and the magnetic field. And that is why it's an E cross B drift, because it's a vector perpendicular to both the E and B field. Of course, the electric field points radially inwards, so this whole time it's going to be oscillating around in an interesting pattern in the planar direction, instead of just moving out in a straight line like this. So there's some math that actually explains this. I don't want to spend too much time on it, but there's essentially these three frequencies that are very important. And you see that the planar motion is somehow connected. So you have this like omega plus and omega minus, the modified cyclotron frequency and the magnetron frequency. And then you have this harmonic motion, which is just kind of on its own, independent of this magnetic field. So we can look at what these single particle orbits look like. And for different ratios of omega plus and omega minus, you get different orbits. So just to note, in our experiment, omega plus and omega minus, the ratio is several hundred. So you basically have tons and tons of these little cyclotron loops on top of this very slow motion around the center of the trap due to the E cross B drift. So notice, in order for this frequency in the bottom here to make sense, this omega plus minus, we want omega 1, this quantity, to be real. So that actually gives us a constraint. It tells us, like, if we're going to trap some charge and mass ratio ion, what field strengths do we need to have? So here's a graph basically showing, like, as I increase the potential strength, the frequencies change. So in our experiment in this spinning trap that I simulate, we're kind of down to the left. But you can see as you increase this frequency or this potential strength, the frequencies kind of close in on each other. So the magnetron motion is related to the E cross B drift, as I stated previously. So another way that you can look at this omega minus, rather than solving the equations of motion given you by the Lorentz force, is by relating it to the C cross B. So it's a pretty neat thing. So another issue that I kind of on a couple slides back said that, you know, the magnetic field confines confinement. I had like, you know, scare quotes around that. Well, it's not really a potential, right? It's basically just causing this particle to like go around the potential at the same fixed radius. So in the way that it's confining it is very interesting. So essentially, anytime this particle interacts, say, with like background gas, like runs into some neutral in the trap, that's on average just going to cause it to increase its magnetron radius. So this is an inherently unstable motion. Luckily, though, you can isolate the system well enough that you can trap a single ion for days or weeks. So it might seem like an issue at first. So our actual experiment that I'm simulating is just down the road. So if you haven't seen, there's this beautiful campus in this, and they have a lot of government buildings and very interesting experiments, some of which you guys may someday, you know, be part of or already are. So over the weekend, I got a tour from John Bollinger, the person I work with in this, and I got to see this experiment since it's taken it apart now, and they're trying to increase the vacuum chamber strength and do a bunch of diagnostics. I got to see this, so we'll get to see in a couple of slides pictures of this. Yeah, so this is what the thing actually looks like. It's quite small, so you can see like this diameter of the cylinder, the pinning trap is like 2 centimeters. And then there's this really big apparatus on top of it, which provides the vacuum chamber. And then this whole thing fits down inside of a superconducting magnet, which is actually rather large. And if you don't know, 4.5 Tesla is a very, very large field. So this thing is highly magnetized. So this is a picture I took over the weekend. You know, it's one of the reasons I enjoy doing, you know, more theoretical work, is I don't have to worry about tools being ripped out of my hand or things like this. But this magnetic field is actually quite powerful. It's very exciting to see these things in person. If you ever get a chance, you should go visit like a BEC lab or perhaps the NIS experiment. Beyond what I've shown, there's also another field, which is this rotating wall field. It really matters for multiple ions. What it allows you to do is tune the shape of a crystal, so and lock its frequency. So there's these oscillating electric fields which basically fix the crystal's rotation in place. And tuning these parameters, you can get, as shown in the video, a blob of ions down to a disk of ions. We'll talk about that. So I just want to make a few points about just the scale of this thing, because I find it really interesting. So I mean, the magnetic field strength is 150,000 times that of Earth. I mean, I guess Earth's isn't that much, but it's enough to get people navigating. So it's quite interesting. And the actual frequency of rotation of this crystal is 180,000 kilohertz. And the diameter of the crystal, so the thing you're imagining, this big superconducting magnet, and this little 2 centimeter cylinder that slides down inside of it, it has in its core a crystal which is about the width of your human hair. So if you pull out your hair and you look at it, it's about that wide. Okay, so now that we all know what a pinning trap is, let's discuss laser cooling. But first, what might happen in this pinning trap if we have ions that are just going way too fast? Okay, so they might shoot out. Yeah, it won't be contained. And what might happen if I have like a crystal and one of these ions in the crystal just gets way too much energy, say it runs into like a neutral or something. Yeah, exactly. Yeah, so we don't want that to happen. We want to slow down these ions. So this is going to be my attempt to explain Doppler laser cooling in a very fundamental way without making it more complicated than it needs to be. But essentially what we got here is we've got some ping pong ball launcher. And we've got someone riding in the back of a truck who's going to catch these ping balls, right? Okay, so this truck has some quite large velocity and great momentum. And then the momentum of this ping pong ball probably isn't as great. So you might imagine if she's just catching these ping pong balls and loses that momentum, the truck loses that momentum of the ping pong ball. It's going to take many events of this in order to slow down the truck. But that's okay because the actual catcher in this case is an atom and the actual ping pong balls are photons. And so this process can happen, hundreds of thousands of times a second. So this is kind of what the catcher looks like. Physically, we have a two-level atom, which we don't need to worry about what exactly that means. But essentially, either it has a photon or it doesn't. So it's caught the ping pong ball, it hasn't. So it goes through a state of catching this laser light to then emitting it. And once it catches it, it loses that momentum of the ping pong ball, slowing the ion down. And then it emits it again in some random direction. So it can't hold on to it forever. So the important thing here is because it emits in some random direction, on average, the momentum is zero, right, if on re-emission. So it's losing momentum in that one direction going towards the ping pong launcher, but it's not gaining it once it throws it away because on average it's in some random direction. So basically that's just this statement. Now notice that even though the average of the momentum might be zero because it's randomly emitted, the square or the second moment isn't. So I mean, I guess just imagining that you've stopped, you're still catching these photons, and so you throw them and you move a little bit. So there is some heating effect, but it's quite small. So now how do I control when the catcher catches these photons, right? Because if the truck comes to a stop and I'm still catching ping pong balls, eventually I'm just going to start heading back the other direction. So how do I actually control that? Well, you can control it by detuning the laser light from this transition. So essentially the atom only wants to see a certain velocity of ping pong ball, let's say. It's a bad analogy, but let's say. And so if I'm going too slow or too fast, this atom won't catch that ping pong ball. And so basically using this effect called a Doppler shift, I am able to make sure that the atom is only catching ping pong balls when it's moving towards the laser. So this is how it's implemented in the experiment, at least in the axial direction, is I have two lasers pointing in opposite directions. And so no matter which way this ion goes, is moving towards one of them, at least in the z direction. And if we just look at like a graph of the single ion and the simulation cooling, we started out with some very large energy, so that corresponds to fluctuations in the plane. And then after many cycles of catching these ping pong balls, which each have very small momentum, I lose my kinetic energy, and eventually I start to get closer to the trapped center. And so that's basically what this graph is showing. In the planar direction, remember this whole thing is rotating. So it's a little bit more complicated. That's actually the hardest part of my research. But essentially what you do is you have some laser beam coming in at an offset from the trap axis. And then you also have some width of that laser beam. And so this is basically showing how the cyclotron and the magnetron motion cools. So I start out with some very large energy and I apply with the correct parameters, this width and this displacement. And I see that the magnetron energy decreases, so this thing spirals towards the center. That's what's happening here. And the cyclotron radius decreases. And so as you can see on the outside, I've got like this very large circles and they shrink down. And I just have, this line is basically going spiraling inwards. So just focusing on the cyclotron motion, which it cools very rapidly. So see the magnetron motion cools quite slow compared to the cyclotron motion. We have in the beginning this really large oscillation that eventually dies down as this thing interacts with the laser beam. Okay, so now we've discussed single ion and laser cooling, and we're ready to move on and talk about ion crystals. So what do you guys think of when you think crystal? Like what pops into your head? What kind of system?
Why don't you turn to your neighbors and discuss this for a few minutes? And then while you're doing that, if you want, we can get pizza in the back. I think, right? Yes, okay.
I feel real sad.
All right.
Oh.
So now that you guys have pizza and you can think clearly again, brain is recharged. I guess, does anyone have anything they'd like to share about what do you think of when you hear the word crystal?
I think of like the horoscope girls who are like, I'm a Gemini and I got quartz crystals. That me with psychic energy.
So perhaps the brain type is similar to that in the sense that it's not the crystal you're thinking of. Probably not anyways. We've got a different kind of crystal. But essentially what we're gonna talk about is, a fixed arrangement of ions in this trap. Of course, it's kind of complicated because they're rotating around at 180,000 times a second. So it's probably not the crystal you're thinking of. But essentially, there's a condition when the coulombic energy between these ions decreases sufficiently, increases sufficiently compared to kinetic energy, or the same way, if you cool the ions enough that the kinetic energy is very small, then this crystal will just begin to become fixed and organized. Otherwise, it's almost like it's been melted and the ions can just kind of slip around each other and change places. So that's basically the condition. I make this thing very cold, and hopefully I get a crystal, maybe some horoscopes. So potential ion, and the potential in the rotating, in the lab frame is kind of complicated. I'm not going to explain all of this because it's just a bunch of math. But this is kind of the issues that we're talking about, right? Like I have this rotating wall and it fixes this rotation frequency for me, but how can I talk about a crystal if I've got a potential that's changing all the time? Not just that, I've got this trap, and I told you about this trap earlier. It's unstable in the radial direction. How can you have a crystal when it's completely unstable and just fall apart, right? Well, the magnetic field helps us, and so when we go to a rotation, this is just some math, we can change this potential to actually get something that we can minimize. So we can minimize this potential over the coordinate positions of the ions to find what this crystal looks like. And that's a very nice thing for us. So you notice here, we've got a positive, our radial direction is positive, so X and Y, this thing is positive, that's very good. And our rotating wall, if we're at the rotation frequency of it, we just see it as fixed, right? If we're rotating along with it, it doesn't change. So now we're just going to talk about these parameters. So this rotation frequency changes this parameter beta, which if you remember, beta is related to this trapping potential. And it also changes the morphology of this crystal. So if I have a very low rotation frequency or a very small beta, then the radial confinement isn't that great, and this crystal will just kind of expand. And expand enough, we can get like a flat plane. If I increase this rotating wall frequency, I can increase the density of this thing. I get like some ellipsoidal thing. So once we've chosen our parameters, in this case, we're down here with some small rotation frequency for the rotating wall. We can go ahead and solve numerically to find the positions of these ions. So just a quick side note, if you have like 100 ions and they're all interacting, and someone asks you to minimize this function over all of the ion coordinates, it's actually a difficult problem. It's actually a fun computer science problem. So there's many ways of doing this, but if you're interested, ask me. Anyways, once we've solved this problem on a computer, we have the ion crystal, and we're ready to set it up we have the initial condition for our simulation. So this is more what I do, like I linearize these dynamics, because of course the Coulomb interaction between these ions is nonlinear, but it basically means that these motion, like if I displace these ions like twice the distance, then the force on them drops off as 1/4, right? Like it's saying that if I have like some input and the output is not proportional to input. So I basically linearize this by taking a Taylor expansion and ignoring all the complexity of the Coulomb interaction, so that I can get something that's easier to study. Because one of the things that you'll realize in research is nonlinear dynamics of many interacting bodies is very hard. And when you throw in a couple lasers and you turn them on and see what happens, it can be very hard to answer questions. So the physicist's best friend here, the Taylor expansion, rescues the day. Of course, it's probably not a form you've seen because it's over all of these coordinate positions. It's not one dimension, but it's essentially the same idea. So once I've done that, I can now consider, these collective motions of these ions. So like if I just have these ions set up, what kind of motions are possible to be supported on this ion crystal? And there's a bunch of math here. It's not really important, but I can think of these motions as kind of representing, any possible configuration, being some of these different motions. So this is just a video of one such collective motion in a comparison between the linear-nonlinear simulation. So you can see if I initialize the linear simulation, it's just going to do this forever. It's never going to change. It's always going to have the same frequency. There'll be no interaction between the ions that causes this to change ever. Whereas you can already see like the red is different than the blue, or the nonlinear is different than the linear. So there's already something happening to this mode. So there's a bunch of different modes that we can express our planar ion crystal in. And they relate to these three frequencies again. So remember at the very beginning of the talk, we had this axial frequency omega z. We had these planar frequencies omega plus and omega minus. And here we have different groups of collective motions related to these frequencies. And they're each at or around these frequencies. Most important are the omega minus, which are up here on the top, because they correspond to large position displacements, which is when the Coulomb force is nonlinear. Coulomb force, of course, just depends on this position of the ions. I think it's probably simplest just to look at the axial motion and imagine how these motions look. But one such motion is in the upper left, and it's just all these ions moving up and down at the same frequency. And so it's quite interesting. But you can have another motion where all of these ions kind of tilt back and forth, kind of like water sloshing in a bucket. You can also have some motion where now you've got like a potato chip shape, but it's oscillating back and forth. So it goes down on either side and up on the other two sides. It just kind of oscillates back and forth. So we can understand our crystal in terms of these motions. So if I initialize some motion, due to the nonlinearity of the problem, it'll excite all these other motions. And so, if I start like a tilt mode that's just sloshing back and forth, I may get, some ion that's just doing, a weird thing like this. Or in this case, if I just take the lowest frequency mode, which is here, which is here on the bottom on the left, and I excite it, then I'll have energy redistribution so that now all these other modes are becoming excited. This issue actually makes it difficult to study Doppler laser cooling because you don't know how the laser is affecting individual modes. So that's why the linearization is important. So just comparing, if I start with some linear simulation, like on the bottom, I initialize some mode to have some energy. Its energy never changes. But if I have the nonlinear simulation, its energy is going to fluctuate. And if you've seen a power spectrum before, great. If you haven't, don't worry about it. It's basically saying that this motion has different frequencies. So if I look at the blue line, there's only one peak, and that corresponds to the one mode I've excited. But if you see the green line, there's different peaks, and this corresponds to the fact that this crystal is exciting other modes of motion. So this is kind of a fun demonstration, but I can initialize each of these modes with a different energy. In the linear simulation, their energies never change. In the nonlinear simulation, you can see there's very complicated things happening that might make it difficult to understand your laser cooling process. But importantly, there's two straight lines. And so those are actually related to center of mass modes, but the whole crystal is moving. Each ion is basically living in its own pinning trap. You can think of it that way. They all have the same motion, so they all oscillate around in some circle. And of course, if their relative position doesn't change, then the Coulomb force between them doesn't change. It's constant. Okay, so basically to wrap things up, this is a simulation of the planar laser cooling, and we've got the difference between the linear and nonlinear simulation. So as you can see, like in the top, there's this magnetron motion because of the E cross B force we have, or because of the Coulomb interaction, we have like these, very erratic wiggles where the modes are transferring energy to each other. Whereas in the Scion, we don't. It's basically just a straight line. And then of course, the cyclotron modes all just kind of cool the same way. It doesn't really matter the simulation. But if we carry the simulation out further, we see something kind of interesting. The linear simulation, its energy just keeps growing. And in fact, if you look at the differences between energies of each mode in the linear-nonlinear simulation, we see that one mode is just taking all this energy from the laser in the linear case. And so in the nonlinear case, this mode would just give up its energy to other modes, right? Because it has that interaction. In the linear case, it can't do that. And so since it's coupled to this laser beam, its energy just keeps increasing. So now we've learned that the laser beam, it interacts with this mode and heats it. And furthermore, the coupling of the modes is a cooling mechanism for the laser cool. So possibly if you were smart enough, maybe you could pick some modes that are coupled to the rest of the modes and just select them effectively with the laser to cool the whole crystal. So this basically wraps up all the research. Now I'm gonna, try and share, who I am, what I do, and what I wish someone would have told me when I was an undergrad. So I'm from Arizona. I really love outdoor activities. I like hiking and biking and riding motorcycles and things like this. I went to the University of Arizona where I studied math and physics. And I think an important takeaway from this is that I did not start out studying math and physics. I actually started out in a biology lab, working with ants. And then I was like, maybe I want to do like computer science or something like this. So I did like simulations of these ants. And then later on I did, atmospheric research. And so I bounced around a lot. And eventually I settled on math and physics. But the important thing is, if you're not sure what you want to do, just try a lot of things. It works out, and you'll learn things about yourself. You might not realize you have some passion, but you'll only find out if you try. I also did this NASA space grant, where first I did research, and then I actually got to be a mentor and help other people going through the program. And then finally I had an RU, which was a lot of fun. Currently I'm a second year graduate student. So the first year was kind of weird because I was in Boulder, but I wasn't really in Boulder. I didn't have the opportunity to meet any of you, unfortunately. But it's a new year and I'm really excited. So basically, I think it's important to remember that everyone's life is going to be different and like how they do things is going to be different. But I start out with, yoga and eating breakfast and making lunch. Then I ride the bike to school, and then things kind of just diverge from there. It can be really random. I think if you're an undergrad, you know what I'm talking about. You're just kind of doing stuff all the time, right? But I always stop for lunch. I think that's important. I always find time for lunch. And then once I'm home, I have hobbies. I think that's another important thing. When I was an undergrad, I thought that you were basically just going to do physics and you were going to focus on physics with all of your passion, all of your energy. But you know, I sometimes go home and I play keyboard until my neighbors get it. Or 50% of the time, I might just read quiet. So that's an interesting thing. The night walk is something that I've been doing for quite a while now, but essentially before bed, you know, it's good to just go on a walk and think about life and, you know, look at the stars, especially when you're here in Boulder. Things are very, very pretty. Yeah, and then sleep. I guess the important thing is no matter what your schedule looks like, and of course it's going to look very different than mine, just take care of yourself. I mean, no one else can do it for you. And it's a very important thing. So have hobbies, have friends, and do all sorts of fun stuff. So if I went back in time and gave myself any advice, I would say do an RU, which is a research experience for undergraduates. Talk to as many people as you can. Go to your professor's office hours and talk to all your friends and see what they do. And read, especially Quantum Magazine. I think it's a really good, interesting magazine that has a lot of variety of topics from STEM. So just because you're doing physics or just because you're doing computer science doesn't mean you can't be interested in other things. You can, you know, keep reading about all the interesting things happening. And finally, to close and wrap everything up, there's these 4 golden lessons from Steven Weinberg. I think these are really important. So in graduate school, you're going to be surrounded by people who know a lot and they're experts. And for the first time, you're no longer in a class where you're expected to know something and take a test on it and get a good grade. You're expected to do your research, and you're going to be surrounded by people who do their research, and they're going to know so many things, and you might feel kind of scared, like you have to know everything. That's not the case. At some point, you just go out there and you just start doing something. Importantly, forgive yourself for wasting time. If people knew what the correct answers were, they wouldn't need you, right? So you're going to possibly work on something for quite a long time and realize it doesn't work. And you just have to understand that's part of the scientific process. If people knew what worked, then you wouldn't have a job. Okay. So don't be afraid to try something new. And then this one is something that makes Steven Weinberg, I think, stand out as a character to me is if you see a place where people are really debating and really don't know what's going on at all, that's where you should do your research. That's something that you should focus on. And finally, I think this is very important, at least for me. Learn about the history of physics. See where your life fits in to a grand perspective, I guess. Okay, that basically concludes everything I wanted to talk about. I appreciate you guys for coming, and I'm really hoping to be here if you have any questions or hoping that this talk helped you in any way. Thank you.
So we have plenty of time for questions. Before we do that, just a few announcements from us. So if you're here in person, be sure to sign in on the laptops if you haven't already. Before you leave, go ahead and do that, just so we have numbers for how many people we should get pizza for, etc., that sort of thing. And for everyone, whether you're on YouTube or here in person, go ahead and take that quick feedback survey. So we really value your feedback on how these talks go. And so there's a URL right there. There's also a QR code you can scan with your phone and do that. And finally, if you yourself are interested in giving a CU Prime talk, then we have plenty of open slots this coming spring. So be sure to email us that email if that is you. Yeah, were there any questions for Wes?
Yeah. Small question,
Sure.
but like I was looking at the math really early on, and I just kept thinking, what is Y?
Oh, the electric potential, right.
Okay, yeah, that makes more sense.
There's too many quick things to go back, but it's fine.
Yeah,
Yeah,
I'm
I
so
find it.
confused because I normally use this thing like Y as plus.
Right.
Like, what?
It's fine. Okay. Sorry about that. There's not enough Greek symbols. We need more Greek symbols. Right.
Is there more questions? Yeah.
Sure.
So when the minute photon
So in my simulation, I ignore this effect, but you're absolutely right. The thing to remember though is that these atoms are like, spaced pretty far apart compared to their relative like diameter, right? So if it's just randomly emitting photons, it's very unlikely that they're gonna like, be pointed at each other. So it's a very small effect, but it does exist. It's photonic, it could bounce around. It's just unlikely they'll ever interact with another photon again, or atom again. Sure, Marvin.
So you mentioned like there's some parameters where the thing will crystallize.
Right.
So how do you know, like in your when you're saying initialize acceleration, how do you know that you're in the crystal phase if not
Well, that's a very good question. So I just take it as an initial condition. I say, wait, this is my potential. I'm going to minimize it to figure out where these equilibrium positions are. And then I just need to figure out what the correct velocities are to start this thing out in the rotating frame so that it stays fixed. So it's actually just an initial condition. But this is one of the things you can study is because you're right. If you give this thing the wrong initial condition, you might have like a molten crystal or a crystal that melts. And it loses its order.
So when you said you use or I guess simulated that time power towards the magnet towards trapping the laser. Is there any? Is that like the specific minimum you needed to trap the laser, or can you use like less high power magnet?
So yeah, there's other experiments that don't need superconducting magnets of the sort. It depends on what you're trying to do. It just turns out, and that's for this experiment, this is what they need, or this is what they want for the kind of crystal that they're forming. So I guess it really relates to ion species, and also, it helps in this case because they want to be able to tune this thing to have different crystal structures. So it gives them a lot of room, I guess. That was our question.
Yeah.
Yeah.
What's the one for your reasons? I mean, is there any applications?
Yeah, exactly. Okay, yeah. So I mean,
Could you repeat that question?
So what is the application? So why do we want this crystal? Well, one, it's really cool. Two, you can actually get interacting ions. You can use something called optical dipole force, and you can get the spins. So this quantum degree of freedom of these ions to interact. And you can simulate, for example, like an Eigenmodes. You may not know what this means, but essentially you can use this as like a quantum simulator to simulate some physical system in a very nice isolated environment that you can study. So that's one of the possible things. There's also something called quantum meteorology or quantum sensing, but essentially you can use it to measure very small electric fields and things of that sort too. So you could even use it as a sensor.
how many ones do you have at once? I mean, your simulation
Yeah.
is like 7, right?
Right. Yeah. So in this simulation back here, oh, I wish there was a quicker way. Okay, like this is 61 ions, and it's usually hundreds of ions. That's the appealing thing about this stuff is you can have like hundreds of interacting spins potentially, which of course I won't go into details, but if you wanted to simulate the quantum nature of this, you couldn't do it on any computer that exists on Earth. In fact, you wouldn't have enough raw material to build a computer in the first place using the entire planet. So it's kind of an appealing thing for that, but to get it to work, you need to cool things down.
When the stuff that you're studying with like 7 ions, does that extrapolate nicely to like 60 or 100?
Yeah, actually, some of these modes, like the center of mass modes here, they also okay. This is. I think there's like intermittent lag. Anyways, these modes exist. So like, for example, like you have this collective motion where I go like this. You may remember like the center mass mode in the axial direction also exists. There's also tilt modes. So yeah, this kind of mode morphology, I guess, like generalizes. Yeah. But if you want to know a question related to that, how do the laser cooling parameters change given the number of ions? That's my research. I mean, that's an interesting question. It's kind of difficult to actually get this thing to work. And you might want to know what parameters make it work. So that's a question I'm trying to answer.
I mean, I can imagine for a larger N, like more than 20 or so, it's kind of big.
Yeah, it is a molecular dynamics simulation. So I mean, 100 milliseconds takes about 4 hours or something like this. But that's generally enough time to simulate the cooling process.
So I guess this one is a more of a personal question for you. So exactly was working as a NASA mentor?
So yeah, the NASA space grant was a really quite a fun experience. So yeah, the question is, what was it like working NASA space grant? They basically fund you for a year to go out and do research with some faculty on your campus. And what I did was atmospheric research. And so I studied things that, I still read about today because, you look at the weather and you're like, oh, I recognize this, this oscillation in patterns. So it's a very fun thing. It allows you to do research. And if you really like it, like I did, you can actually become like a mentor and, help people do their research, which for me meant helping people use code editors, text editors and things like this, or, just find a good place to study sometimes. Yeah.
I noticed on your thing you only wrote debugging once.
Okay, this guy is obviously programmed before, so yeah, debugging is like most of what I do, if I'm being honest. So yeah, that's fun.
Well, if there are any more questions, you can come up and ask Wes individually afterwards. But let's thank him one more time.